14.3. We're going to talk about limits and continuity. Here we go, right? So this is the world of 3D, right? And so I think I gave you guys the link to GeoGebra graphing software, and a couple of people signed up, yeah? So, yeah, MySpace for math, right? So here I am. This is a blank GeoGebra file, and so I'm really trying this on the cuff right now. I want to see, does it work? Okay. I've had a little success, but not a lot. Here I go. F of x comma y, right? Those are functions that are multivariable functions. We're going to have two inputs. And so my gray is the xy plane, right? And so if I want to talk about an inputs and output, then I can say equals, right? And say, how do I determine the z coordinate, you know? And so we can think of ways of doing this. So maybe we say 2x. Does that make sense, what I just did? Why does it look the way it does? Yeah, okay, well, let's look at x. I mean, do you know what that looks like? If I say f of xy is always equal to x, why is it a plane? Well, I guess because the z is the same as the x, but the y can be anything it wants, right? So I guess if you want to get interesting graphs, give me something else to use for an input. X squared, okay. Hey, there's a parabolic cylinder, you might call it, right? We called it, or a paraboloid. And of course, remember that was the problem last time.
That's the thing, I call it a parabolic plane.
Yeah, I mean, it's a parabola that you're kind of sliding along the y-axis because y is not even involved, right? So what about this? If I say z is equal to x squared plus y squared, what's that? So is it a cone or a paraboloid, I guess? Yeah, that's the question. What can I do here? I can zoom in. Let me zoom in. I'd like to zoom in. There we go, right? So zooming in gets me a little closer, and I can see it's rounded at the bottom. And actually, this may make sense to you because we talked about something last time called level curves, or no? Yeah, did I? Duncan, do you know what level curves are? Did we do it for e to the x? I don't know. Well, let me talk about it now, okay? So when I have a function of more than one input, okay? So in particular, if you have a function z is a function of f of x, y, can be described by its level curves. When I say that, let me say exactly what I mean by that. I'm saying these are curves defined by taking particular values of z. Of, I'm going to say, the output z. Okay? And so my example, I'll just use the one that I'm using right now. I'll say, suppose you have f of x, y is equal to x squared plus y squared. Then you can give me a particular value of z. So you might say 9 if you're nice. Because if I take z equals 9, then the equation says that x squared plus y squared has to equal 9, right? And so if I wanted to represent that, I could. I could say, well, let's graph it, right? Because what does the curve x squared plus y squared equals 9 look like? It's a circle. So on the xy plane, I know that z equals 9 is a circle of radius 3. Okay. And so in particular, if I go back to the picture, the website, and if I say, hey, I want to graph z equals 9, I didn't like that so much. Well, let me, instead of z equals 9, let me go back to, let me say f of xy. It'll probably like that a little better. F of x comma y equals 9. Well, that's just a plane, huh? Oh, I see. Now it replaced, so I need a different name for it. Let's call it g of xy then. Can be my x squared plus y squared. It's funny how it just grabs more and more as we do this. Well, we should really make these things different colors, hey? Okay, I obviously have a ways to go on this, guys. So you could see, right, once we get above that red plane, you could see the green sticking out. Maybe we'll try another input. If we do f of x, y is equal to 4. There's another nice one. Now it's lower, right? And so you can see that the plane intersects the curve in a circle of radius 2. Or if I say, hey, I'm going to change that again to 1, right? And so one of the things I could do is I could say, let's draw those level curves, right? So we could next do z equals 4. So we have x squared plus y squared equals 4. And that would be this circle. Right. Z equals 1 would be this circle. I could do z equals 0. I guess I couldn't really do negatives, but I could do 0 and I just have a point, right? So sometimes you'll see that we're going to talk about level curves, and that's exactly what I mean in this class. Okay? Because when I'm talking about functions in chapters 14 and 15 of the book, we're usually going to be in this environment. The world of R3, where Z's the output and there's 2 inputs. But we'll do other things too, okay? But this is usually where I'm going to be talking about. So if you see the XY, think of this as the total amount of input possible, right? It used to be just X was input and Y was output. So that's one thing that's different. And so 14.1 and 14.2 mentioned this. But when you get to 14.3 now, we want to start calculus. And if you want to start calculus, you have to learn about limits. And that's where they start, right? Although it's interesting, because as you guys were talking, it seemed like the first thing you guys started with, because of the way it's in the book, right? You guys started with continuity, right? Section 2.6. And then, if you really want to know the formal definition of limit, you go to 2.7. So maybe I'll go in that order, right? I'll talk about continuity, and then I'll talk a little bit about limits. I could do that. Well, maybe it's your call. What do you want to see first, continuity or limits? Flip a coin for that. Okay. What do you know about continuity? Do you guys have a definition? What that means? Oh, that's for limits. The epsilon thing is all about limits. So, yeah, this 2.7. Okay. We'll say the limit as x approaches, let's say a of f of x equals L means, and yes, I had this definition I already wrote for you guys. For every epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. I think I wrote that the first day of class. And when I wrote it, only a few of you were comfortable with that definition, so I have to be careful today about this one. And we'll draw some pictures to show what this means in today's setting. It's done in your book. So, they say, let's talk about the limit of a function. And they say, okay, first thing that's different between, and let me move this so you can compare what's in your book to what I just wrote down, right? I mean, let's really take a look. First thing you notice, in Calc 1, we had x approaching a, right? Because x was the input. But what do you notice about their definition? They have the limit as x and y are approaching some point, right? A and b. You guys see that? So that's one major difference, is that in Calc 1, we talked about the inputs getting close to some number a. And in Calc 2, it's x and y are getting close to a and b, let's say. Okay? Now, one other thing you're going to see in the book, you guys see this? Absolute value of x minus a. Right? Well, now they're going to replace that with this distance from p to p naught. That's just the Pythagorean theorem. But I need to show you some pictures, I think, to show you exactly what's going on here. Okay? This gets a little technical. And this is where I can see why in Calc 1 we did do continuity before we got all that technical. So I think I'm going to do the same thing. I'll come back to this in just a second. This is the old definition. But 2.6, continuity. We say that the limit as x approaches, no, I'll say this. We say a function f of x, this is Calc 1 again, right, is continuous at x equals a if, okay, so it's funny, when I teach Calc 1, that little dot, dot, dot is a quiz question or a test question for my students. And this is also a test question for my students. I want them to know what it means to be continuous. In algebra, we just say, hey, you can draw the function without picking up your pen. That's continuous. But in calculus, we get a little more technical about it because we want to say, well, what's that mean exactly? Do you guys know the definition here from 2.6? Yes. That's exactly it. It has to do everything with limits. As x approaches a, we're trying to compute a limit of a function. Well, you just substitute in. Ta-da! And then it's like, okay, why do I even have this definition? Who cares? And so usually in Calc 1, one of the first things they show you is they try to show you a function that looks something like this. They say, okay, what about this function? Say 1 over x minus 2. That function is continuous almost everywhere, except for one place, right? What's the one place where that's not continuous? At 2, right? Why not? Well, because you can't even compute f of 2. So you should really understand when we write this definition, right? Here's the definition. But really, there are 3 statements in one here, okay? What are the 3 statements? The 3 statements are, first of all, f of a has to exist. Second of all, the limit as x approaches a of f of x has to exist. And then 3, they are equal. So these are ideas from Calc 1 that come back again today. Because we're going to be giving you functions, and we're going to say, well, are they continuous? And we're going to have to know, well, does the limit exist? They're all ideas you had before, it's just that the pictures are going to be a little bit different now. Okay. So, let's show you a very interesting function. We'll have to see if the calculator is going to help me or not. I don't know. But here I go. I'd like to compute the limit as x comma y approaches. I'm going to have to give you an a and a b, not just an a. I'm going to have to give you a point it's approaching. So let's say it's approaching the point 2 comma negative 3. And now I'll give you a function. And the function I'm going to give you is 2x squared y divided by x to the 4th plus y squared. And I do not expect anyone has any idea what this surface looks like. But I will give you a hint. This is an easy problem because the function is continuous almost everywhere. As a matter of fact, where's the only place it's not continuous, would you suspect? At the origin, the point 0, 0, same concept, right? The denominator is undefined, and so it's not continuous there. But since it is continuous, all I have to do to compute this is what? Everywhere there's an x, plug in a 2. Everywhere there's a y, plug in a 3, right? So why don't you guys work on that, compute it for us, and in the meantime, I think I'm going to see if our software can graph this baby. Okay, let's clear all that out. It's all good stuff, but here we go. F of x, y is equal to 2x squared y. Ooh, wow, that's cool. Divided by, and then we have x to the 4th plus y squared. Look at that cool picture, right? So this is some kind of a warped surface. I wonder if I can just plot the point f of, what is it, 2 comma negative 3? It can compute it. Do you guys get negative 0.96? Matter of fact, I wonder if I can plot the point 2 comma 3 comma negative 0.96. I wonder if it'll do that. You see a blue dot somewhere? Over here? Is that it? I guess down here, right? Because it would be 2 in the x direction. Yeah, that's point A over there. You guys see that? I wonder if I can grab this surface and move it. Rotate 3D graphics view. Ooh, yeah, that's getting nice. But why? I guess what I don't understand is why is it that...
You don't have -3.
Oh, I don't have -3?
Yeah, you have A equal to 2, 3,
Oh, so I graphed it wrong. Thank you. Try that again. Let's stick that negative in there. Enter. Okay, good. Now it's on the curve, or on the surface, right? So that's a particular point. Yeah, this is a nice software. You guys will have fun with this. GeoGebra. I don't know if any of you did it for the vector calculus stuff. It does that too, but this is even easier. Okay. So, you guys can compute limits? Well, if they're like that, right? So, what about at 0, right? The question is, what happens? Matter of fact, back to Calc 1 for 1 second. The other example that I like to give people in Calc 1 is a function like this one. G of x equals x squared minus 4 over x minus 2. I always do that one. What's the difference? You do.
Yeah, if you factor the difference of squares, you can make it a lot easier.
Yeah. Or there's this thing we learned later, right, called L'Hopital's rule. So if you're trying to compute the limit as x approaches, what's the hard one here? 2, right, of g of x, okay, it turns out that that's equal to the limit as x approaches 2 of, well, just x plus 2. And so what is the limit? The limit is 4, right? You guys remember doing that kind of thing? And I want to point out that Aaron mentioned something called L'Hopital's rule. So it also turns out that the limit as x approaches 2 of g of x. See, if you thought, oh, I'm going to just substitute in 2, what would you get? You would get 0 over 0, right? Do you remember what that's called? Indeterminate form. And so then there was this thing where you can do the limit as x approaches 2 of, you take the derivative of the top, 2x, and you take the derivative of the bottom, 1. And if that gets you something you can compute, that was L'Hopital's rule, right? So once again, I get 4 over 1, which is also 4. So these are Calc 1 ideas that, again, are handy to have. And they apply, these same ideas apply in Calc 3. Again, I guess the thing I'm getting at is this 0 over 0, right? When you get that, well, it's not continuous because f of a does not exist. But the limit exists. You guys with me? And so if you just said, hey, I'm going to make f of 2 equal to 4, then you can actually have a continuous function. It's what's called a removable discontinuity. All right, but let's go to our problems today and see what's happening. So, I guess, I might wonder, let's look at this function. let's consider the limit as x, y approaches 0, 0, right, of this function. 2x squared y over x to the fourth plus y squared. So what I'm really wondering here is, as we get closer and closer to the origin with our inputs, let me go back to the picture or the graph. What do the outputs get close to? Let's see. I think I should zoom in again, huh? Because I want to get close to the origin. I guess it's kind of hard to tell what's happening at the origin on this one. Isn't that weird? Okay, well, we'll see it a little bit more. I need an example. I need a line that goes through the origin. What do you suggest I use? How about y equals 2x? Of course, it's a plane, right? In 3 space. Do you see that little light blue plane, or is that too light? This is where maybe changing the color might help us, Rebecca. Look at that thing rotate. That's awesome. Oh, that's not how to do it. We gotta change the color. Stop. Okay. See that thing? So the question is, if I move along that line towards 0, what will the outputs of the red surface move towards? That's the question. Okay, well, we can compute it. So, first of all, if you just plug in, what do you notice? 0 over 0. Again, this is indeterminate. If we had gotten non-zero over 0, we would say the limit does not exist. That's another Calc 1 idea. But if you get an indeterminate form, not sure yet. Sometimes there's some algebra you can do, or L'Hopital's rule. Okay. So I need to guide you through some hints here. All right. First exercise, I'd like to do the following. I'd like to show that f of x, y, meaning this thing, approaches 0 as x, y approaches 0 along any straight line through the origin. Okay, here I go. So again, what I'm claiming is, if this is x and this is y, right? So again, these are inputs. And I'm moving along some line through the origin, right? As the inputs approach there, as the inputs approach 0, the outputs approach 0, right? That's the idea. So let's show it. All right, how do I do this? Well, I guess I need to know the equation of this line, okay? Let's assume the line has equation. What would be its equation? Well, give me what's an equation of a line look like? Y equals x, okay. Although this one, that'd be if it had a slope of 1. This one might be a little bit steeper the way I drew it. But yeah, that's a line through the origin. How about I just say y equals mx, and then does that account for every case? Well, the answer is almost. Almost every line through the origin can be accounted for like this. We'll talk about the exception in a minute. Okay, but let's suppose that we have this equation, right? And let me say that m does not equal 0, because that's another weird one. Okay, but if this is true, then here's what we have. Limit as x, y approaches, well, actually, I guess I don't really want y here. I want, okay, let me try again. Limit as x comma mx approaches 0, 0 of the function 2x squared. Now where it says y, I should write mx, right? Because we're saying y equals mx over, and what would I get here? I would get x to the 4th, right? Plus, what am I going to write? Instead of y squared, we're going to write mx quantity squared. You guys follow so far? Well, I think this is something we can actually compute. This equals the limit as x comma mx approaches 0, 0 of what? Looks to me like it's 2mx cubed, right? Over, this would be x to the 4th, right? Plus m squared x squared. This okay? Can I do anything now? Yeah, I mean, we have to factor before we cancel, but you're right. We can cancel. It's just like we did for that other problem. It's just that I'm going to factor out, how much I could factor out an x squared here, and I'm left with x squared plus m squared. And here, I guess I have 2mx cubed. Yeah. So let's see. This is equal to, and here's a trick. I'm going to highlight this one in pink. This is actually equal to the limit as x approaches 0. Because think of it, guys. If you're moving along a line here, and if x is approaching 0, what's x times m? 0. I don't care what your m is. I don't care what your slope is, right? I can do it this way. So then this expression we've simplified and made it what? It's 2mx over what? X squared plus m squared. But I think this is one of the keys here, is that when you change that to 0, you get 0 in the numerator, but in the denominator you get 0 plus m squared. Does that help? Well, it does, because I made an assumption. What was my assumption about m? Doesn't equal 0, right? And so you get 0. So that says, oh, maybe this function is approaching 0 as the inputs approach the origin. That turns out that's not true. We'll see in a moment. Okay. I guess before I move on, I'm supposed to do any straight line through the origin. So I'm supposed to also take care of the cases where you're moving along either the x-axis or the y-axis, right? Because m equals 0, that would be this one. And by the way, let me do the y-axis case, right? So maybe I'll do that in purple. What happens if I'm moving along this line right here? Well, if the line is x equals 0, let's see what my equation looks like. Well then, let's see. Limit as xy approaches 0, 0 of 2x squared y over, what is it? X to the 4th plus y squared. Well, first of all, if I'm on the y-axis, I know one of the coordinates already. Because this line is x equals 0, right? So you could fill in, since I know the x is 0, this is just the limit as y approaches 0 of 2 times 0 squared times y over 0 to the 4th plus y squared. Does it make sense? So I get 0 in the numerator over y squared, limit as y approaches 0 of 0 over y squared. That's a little interesting to me. But 0 over y squared is 0 for any, so it's the limit as y approaches 0 of 0, which is 0. Because it doesn't matter what happens at the point for limits, it matters what happens near the point. No. It's interesting because, and again, this goes back to 2.7. When you talk about limits, the fact that the inputs have to be greater than 0, x, the absolute value of x minus a, what that is really saying is it doesn't matter what happens at the point, it matters what happens near the point. So you don't get this by substituting in, but what you say is, hey, for anything non-zero, which is what we have, 0 over y squared is 0. So it's almost like compute that first, then take the limit. And if you have 0, 0, 0, 0, 0, the limit is 0. Okay, part B to this pathologic example. What happens what about, let's say, if I approach along the curve y equals x squared, right? Everyone knows the parabola. Let's compute the limit in that case. So here I go. Limit as x comma y. Oh, wait a minute. Instead of x comma y, let's write limit as x comma x squared approaches 0, 0. Right? Because we're saying we're actually going to stick along the parabola as we head in towards the origin. Of what? What am I going to write here, guys? Well, it would be 2x squared, because y is the same as x squared now, over what? Well, x to the 4th plus what? X squared squared, right? Which is what? So what I really have is I have 2x to the 4th over what? X to the fourth plus x to the fourth is 2x to the fourth. Right? And again, I should write limit here. So what I really have, guys, is I have the limit as x comma x squared approaches 0, 0 of what? Of 1. And what does that equal? 1. That's really weird. And it's so weird that computer programs like GeoGebra have a really tough time graphing this function. This function, by the way, because you're getting two different limits, limit as xy approaches 0, 0 of 2x squared y over x to the fourth plus y squared does not exist. Kind of like in Calc 1, remember how you sometimes had the left-hand limit and the right-hand limit? Do you guys remember those problems? They had to equal for the limit to exist. Well, this is similar. It's funny, every line through the origin is going to take you to 0. But if you happen to travel along this parabola, you're going to be having a limit of 1. Let me go back to the software and see if we can see that. I thought I glimpsed it. All right, guys, so let's see. There was a particular plane. I was trying to show you movement along a line, and I was going to go right to the origin. You guys see that? But maybe you can see it. Do you guys see this hilltop over here? Do you see this kind of curve right here? You know what that is? That's your curve y equals x squared. And notice I'm elevated. I'm up here at 1. Do you guys see that? So if you move along any line, you're going to be kind of moving down the slope and heading towards the origin. But if you happen to take the parabolic arch, you're going to stay up here by 1. These are phenomena. See that? You can see the sky view. You could really see that little ridge up there. Isn't that cool? I wish I could have learned Calc 3 this way. But I guess what this shows you, oh, look at that, and then it's just like a cliff, you know. It just shows you kind of how nasty things can get. You have to understand, for any other point on the entire input, we're fine. We just plug in, like we did at the beginning. Right? One last example I think I should show. Because it's not that they're all this bad, you know? So let me give you another one that might make you hesitate at first, as it should. But it turns out that there's some nice things we can do. So let's consider this function. F of x, y equals, and I'm going to do something we did in Calc 1 when we tried to make things continuous. You might remember we would put this, it's called defined piecewise. And so I want it to equal the sine of the product xy over xy. That's a real fun curve. I don't know what it looks like, or surface. Of course, this only works if x times y does not equal what? 0. I'm going to say that my function equals 1 if x times y equals 0. So look at this function. Okay? And so what the exercise is to show that f of xy is continuous everywhere. Well, continuous. Almost every function you guys can think of is continuous. Why is that true? Well, first of all, is the sine function a continuous function? Do you guys remember that? Sure. And you can add two continuous functions, it's continuous. If you subtract them, it's continuous. Multiply. Divide could be an issue. Because when you divide, you might get something undefined, like we did here. But what we just did is we defined it. By the way, when we say, where on the plane would the problem spots be? Well, see, if xy equals 0, that's either x equals 0 or y equals 0, right? So I guess what I would say is, obviously, the function is continuous at all points not on an axis. So my problem spots are either when x is 0 or y is 0 or both, right? That pink kind of shows you my problem spots that I have to worry about. So what do I do? Well, I guess what I need to do is I need to say what happens when I'm approaching one of the axes, okay? So if we approach an axis, we have the limit as the product x times y. X times y is going to get closer to what as we approach an axis? 0. And so the question is, what happens to f of xy? Well, this is the limit as xy approaches 0 of the sine of xy over xy. And guys, anytime we can turn a Calc 3 problem into a Calc 1 problem, we like doing that. And I'm going to do this. I'm going to say that z is actually xy. So guys, now this is a Calc 1 problem, I'm saying, because there's only one variable. Z is the same as xy. Right, we'll substitute. Do you guys know what this limit is? It's 1. How do you know? Squeeze theorem is how we proved it in class. That's right. Now we know how to do L'Hopital's. Let's do that. How do we do it? Well, we just take the derivative. Because if we plug in 0 right now, what's the sign of 0? So we'd get 0 over 0 indeterminate, right? So we're allowed to use L'Hopital's rule. Maybe I'll put a little note here. LH. Take it to the hospital, right? The limit as z approaches 0 of, what would the derivatives give me? It would be cosine of z over 1. And what's the cosine of 0? So we get 1 over 1, which is 1. And that's why, look, that shows this is continuous. Why is it continuous? Because the limit is equal to the function, right? That's what you need to have continuity. Okay? Yeah. I am done, guys. I have 30 more seconds, and then we're taking our break, and then we're going to review for exam 1. Math majors would analyze continuity even more than we did, and they would also talk more about limits and the epsilon deltas and all that. Okay, and it's really fun, I think, to look at functions like the ones we did that are really strange. Okay, because if you understand those, then it seems like you can understand just about anything. All right, I'm going to pause here, take a 10-minute break. Well,